Thank you so much for the invite. It's of course, I'm not in Tübingen, but I know what Tübingen's like, and it's such a pleasure to be virtually in Tübingen. Okay, so I want to start with this quote, which is known as Laplace's Demon, and this is the sort of French. I'll do the English in a moment, but it's starting here. Nous devons donc I can't even speak French. Envisager l'état présent de l'univers comme le fait de son état antérieur. But the English of this is a translation, I think, from about 100 years ago. We ought then to regard the present state of the universe as the effect of its anterior state and the cause of the one which is to follow. Given, for one instance, an intelligence which could comprehend all the forces by which nature is animated and the respective situation of the beings who compose it, an intelligence sufficiently vast to submit these data to analysis, it would embrace in the same formula the movements of the greatest bodies of the universe and those of the lightest atom. For it, nothing would be uncertain, and the future as the past would be present to its eyes. Now, this quote is from 1814, and I love how much of like what is the apparent promise of AI is sort of embedded in this quote. It's sort of what he seems to be describing. It's called Laplace's Demons or Laplace's Determinism, but it's more like a sort of super intelligence of the type that we get in, I don't know, Nick Bostrom's books and other things. And the remarkable thing about this is it's also Laplace's determinism, but appears on page 3 of an essay on probabilities. So one might think that's rather odd to talk about a deterministic universe in the world of probabilities. And indeed it is. And I'm going to introduce to you what I call Laplace's Gremlin, that I think is the point of that thing. And Laplace's Demon is actually a straw person. It's an argument that says, well, this can never possibly happen. And I think the fact that we're so obsessed with this quote and people still today are claiming that we can do this type of thing is rather depressing. And I think hopefully the ML for science movement will deal with that, because Laplace is saying 200 years ago, look, don't be silly, we can't do that. So what can we actually do? Well, we can see the different parts of Laplace's Demon in this little sort of formula I have for machine learning, which is you combine data, which is the sort of state of the universe, plus the model, which is your sort of understanding of how the universe works, through compute to make predictions about what you expect is going to happen next. And this, to me, is the fundamental underlying idea of machine learning. And I think it's also the fundamental underlying idea of some other sciences. But I think the interesting thing in machine learning is the emphasis we place on prediction, that instead of interpretability of this model or trying to do this in some way where we have understanding of the system, we tend to have focused on prediction. And that's what makes machine learning, to me, different from other fields like statistics or whatever. Now, this quote, I think it sort of appears again in this sort of Stephen Hawking Brief History of Time, 1988. If we do discover a theory of everything, it would be the ultimate triumph of human reason, for then we would truly know the mind of God. This clearly has to be something you need to put in your cosmology book if you want to sell it very well, because this is the sort of thing that everyone, I think, thinks of when they think of that book. Whether they understood the rest of it, I can't remember the last time I tried to read it, but I certainly didn't understand it when I was sort of 12 or whatever, and I tried to read it. But what a great quote. And it's very close to what Laplace's Demon is saying there. And so I think what I want to see is, well, why is that not true? Why is that kind of, I mean, it's clearly interesting to know the physical laws that underlie the universe, but I want to use this example to sort of show that this is clearly wrong and a mistake to think that way. And the example I want to use is I chose this picture of John Conway because I think he looks a little bit like God here. And what we are showing is a universe which he is God of, because what I'm going to sort of talk about is the game of life. So the game of life is a cellular automata that Conway proposed. And in Conway's game of life, the idea is, I'm not great at sort of depicting what goes on, but some 3 very simple rules. So the game of life is played on a grid where there's black and white cells. And in my case, black is alive and white is dead. And in each turn, it's played in turns. And in each turn, what happens is there's no players in this game. It's a 0-player game. What happens is any cell that has only 2 neighbors. So the important thing for this cell in red is what the cells are doing in the neighborhood around it, the 8 cells around it. If that cell only has 2 neighbors or less, it dies of loneliness. So any cell that has 2 neighbors or less dies of loneliness. There's only 3 rules to the game of life. The next rule is if there's 4 or more cells in the neighborhood, then that cell will die of overcrowding. And so in the next turn, that cell disappears. By the way, something would happen to the cells around it, which I'm not visualizing here to give you the sense that this cell has disappeared. And then the third rule is birth, that any cell that is surrounded by precisely 3 cells will either persist because it won't die of loneliness, it won't die of overcrowding, or if it doesn't exist, it will appear. So you get birth. So 3 extremely simple rules. And this goes right to the heart of what Laplace and Hawking are saying. In this universe, Conway is God, and he's defined the physical laws of the universe. And there are these 3 very simple rules. And already things start going wrong. And the things that I want to describe what's going on is that, so Conway described this in, I think, 1969, and it was published in 1970, but a collaborator of his, whose name I forget at the moment, early on, showed that, I mean, Conway was trying to design a cellular automata with simple rules that leads to complex behaviors, that these rules lead to things like this. This is, I think they call them spaceships in the game of life, but this is the simplest spaceship, and it was discovered very early on. It's called a glider. And it's a pattern that, because of those rules, and each of these cells is obeying those rules, moves diagonally across the screen. So it's moving diagonally down, but because of symmetries, it could move diagonally up to the right or up to the left or down to the left. And this was discovered very early on. And what people have done using this pattern itself as a sort of as a method of encoding information. So you can take the presence or the absence of a glider at a certain point as a 1 or a 0 in a bit stream, is they've built Turing machines in the game of life. So basically the game of life can compute anything, which is rather remarkable given these 3 original rules. But this is an emergent pattern, and it's this type of pattern that we care about. So this becomes an object. So in the real world, we might care about hurricanes. Hurricanes are a consequence of Navier-Stokes equations. But when you feel the force of a hurricane, you're not feeling directly the force of the Navier-Stokes equations. You care about the hurricane rather than the details of the laws. And in the game of life, you care about things like the glider. And you get to this sort of problem that there are patterns that can appear in the game, and this one's called a loafer. It's a spaceship that moves to the left more slowly than the glider, or to the right, or up or down. That took 44 years to discover in this universe, which is entirely controlled by Conway, or has entirely defined by Conway. So Conway is the god of this universe. So knowing the mind of God in that sense gives us some form of omniscience in terms of we understand the physics behind the entire universe. And yet we still take 44 years to understand certain patterns that can appear within that universe. Now imagine when you take that and you deploy it in our universe, and we still don't understand the full physics of the universe, and the complexity of those underlying laws is much, much greater. And the things we care about, again, are phenomena like the hurricane or the volcano, not the underlying physics. And that's the problem we face when we're trying to do machine learning in the physical world. So it's nice that we can try and reduce all laws of the universe, as sort of Conway did in this world, to something much simpler. But what we're really trying to do is use machine learning in this domain to help people understand the phenomena we care about, in this case, the loafer or the glider. Okay, so it's crazy that that Laplace is so famous for Laplace's Demon, for Laplace's determinism, because that's page 3 of his essay on philosophical essay on probabilities. And the important thing about that essay is on page 5. And so I've decided to call this Laplace's Gremlin, because it seems that if you call something a demon, then it sticks with everyone. But the real point in that essay is this: the curve described by a simple molecule of air or vapor is regulated in a manner just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge, etc., etc. So it's less pithy, but now I want you to all remember this: Laplace's Gremlin. So that's the fundamental thing that we're trying to deal with. The uncertainty means that we can't do all of those things. We don't know the location of everything in the universe. We also don't know the physical laws. And even if we take a universe, as I just have done, Conway's universe, and we look at how that universe plays out, we don't have all the compute that's required to say precisely of what's going to happen. things still happen through uncertainty. And I know I'm preaching to the converted here, because if you look at, say, the probabilistic numerics agenda that Philip Hennig and others are looking at, this tries to look at all these things in terms of uncertainty. We make decisions around computational, around missing data, around not understanding the physics that use uncertainty. So the true message that Laplace was trying to portray is that you have to deal with these things through uncertainty. And to me, what that also means is that by introducing a stochastic element, you introduce an element of stochasticity that allows you to abstract your universe. So you can talk about a hurricane, even though the hurricane is the result of Navier-Stokes equations and interactions between sea and land and atmosphere and everything else. But the entity of a hurricane does things that we talk about in a more abstract level. And there are aspects to that hurricane that we just explain away as stochastic, even though we know they're fundamentally deterministic. And that, to me, is the art of being able to answer the type of questions we want in science. So that's my philosophy. So remember that. It's the gremlins that do things to you. I mean, gremlins, for those that don't know, the history of the gremlin originally is it was invented by pilots to explain why their planes kept crashing. It wasn't down to bad maintenance, it was due to gremlins interfering with things. So how does that relate to the history of what we're doing sort of machine learning now? Well, I saw this statue, the building behind it is on Holborn Viaduct in London. And I love this statue because it says science at the bottom. And I think it's sort of 19th century at some point, Holborn Viaduct, late 19th century. But it's a picture of science and what science is holding. Does anyone want to type it in to the chat? Does anyone know what science is holding? It's a very important object. You can see people typing, so I'm just going to leave that there. Astrolabe, no. Scale, no. Look at this. Oh, a governor, a governor. Thank you very much, Philip. Science is holding a governor. Yeah. So what science is holding is a centrifugal governor. And I just think this is so amazing if you just portray what's happening in the late 19th century, that when they think of science, they are thinking of the centrifugal governor that Watt designed in order to control the steam engine. So we'll just tell that story for a moment there and what the essence of that story is here. So James Watt, of course, didn't invent the steam engine. Newcomen had a practical engine that operated before then. This object down here, the separate condenser, here's the cylinder, is one of his major innovations. But he made many innovations. And one of the innovations, he actually copied off windmills. So windmills used centrifugal governors to engage the two stone wheels that actually grind the corn. So what happens in the centrifugal governor is you have a spindle and the balls start spinning and they go out. And when they go out, they can be used. The higher the speed in the centrifugal governor and the steam engine, you close down the valve. In the engagement of windmills, the higher the speed, you engage the stones to start grinding the corn. So it's a sensing device that senses speed, and it's got an input, which is the sort of speed from the spindle, and it's got an output, which can be used to either bring those stones closer together or close down the steam engine. And it was called a governor because it pervades the same role that a governor does. Originally, the Greek word is like a helmsman of a ship, so it's someone who's steering the ship. We're using the Latin word governor, which is a corruption of the Greek. And so there's a sort of representation of it. Now, what I really like about the governor is, in some sense, you can look at it and it's an abstraction of the steam engine. So what the governor's having to do, because all sorts of problems occur with the governor, it's making a decision about when to shut down the sort of throttle of the steam engine according to what the input is. And, people like Bob in the audience will know all about control theory and how you prove the stability of these type of systems. But if we really distill it down to its essence, what you're trying to do is represent the essence of the engine you're interested in by things like the weight of the balls you use in the governor, because that gives you the inertia, that gives you the properties of the function. There are a number of parameters all being marked out here, in this pivot and so on and so forth. And those are the parameters of this little system, which in some sense is distilling the essence of the steam engine that we need to control it into a subsystem that is an abstraction of that steam engine in some pertinent way. And my argument is that this idea is at the core of a lot of what we need to do in machine learning for science. It's not the only thing we need to do, but it's something I'm very interested in. So here you can see, by the way, you can see the lap engine where Watt first installed the governor in the Science Museum. It's a beautiful thing. It was actually installed first at the workshop. It was Bolton, his partner, who first saw the gear and mentioned it to Watt, and Watt put it on this lap engine, which they installed in their workshop for lapping, which is a activity they were doing. He also, by the way, invented this sun and planet gear mechanism because the connecting rod was patented, and so he didn't want to pay the patent fees. So that's why there's a funny gear thing down there. Okay, so there's a gap between, I think, the world of data science and artificial intelligence and the mapping of that onto from the virtual onto the physical world. And in terms of what we're doing at the moment, which is mainly data driven, like here's some inputs, here's the outputs. And that gap is leading to things like a failure to have a causal understanding of the systems we're looking at. And to me, the interesting thing about this agenda of machine learning in science is how we can try and pull that gap back together. And the technology I would like to sort of push as an interesting direction to go in for pulling that gap back together is what I would call statistical emulation. So this is not originating from machine learning community, it's in the applied maths community and several others, but I just want to highlight what it does and how I think machine learning people can get very involved in this agenda. So to just introduce, before I go too deeply into that, I want to just introduce this plot here, which I'm afraid is a bit too small to read, but what it's trying to show is all the different models that they run on the UK Met Office's supercomputer for predicting the weather and the climate. And what it says across the bottom here is forecast lead time, and that's starting on the left-hand side, it's going up to 48 hours, 7 days, 15 days, 6 months, 2 years, 20 to 100 years. And then on the y-axis, what they've got is grid length, and that's starting at 1.5 kilometers here, and it's going all the way up to 300 kilometers. So what this is basically showing you, and it's very, I think it's an odd thing, and I don't think personally I would design things to do this, but they're quite proud of it at the Met Office. The same code base runs the same physics on the same model at all the different scales of forecast lead times and spatial scales as well, which I'm not sure I would do it that way, but it's the way that they've gone. And it's really useful for me to have that in front of me because what we're showing here is basically different simulation fidelities. So they've got the physics, they believe they've got the right physics, and they're running this physics at different fidelities. Why are they doing it at different fidelities? Because it takes too long to do it at the finest fidelity. So basically, I think the morning is spent doing the weather forecast, which is sort of probably up to about 7 days, and will be across a few different grid lengths in order to do the UK forecast, the European forecast, and the weather and the world forecast. And I think the afternoon, then you're looking at doing the climate forecasting, running climate models to try and predict the effects of our interventions on the climate, all in the same code base. So where does machine learning come into this? Because this is just a sort of pure set of physics models. Well, this is where emulation comes in, because what I'm representing in this picture is the idea that we have these different simulators. Now, I would say this is quite different to what's going on in the example of Watt's governor, or the centrifugal governor, because in the centrifugal governor, what you're doing is you're distilling the essence of the engine into this sort of this mechanism that is not actually replicating precisely the physics, it's replicating the essence of the physics. Here, these simulators are trying to replicate the physics itself. They're just doing it at different spatial and temporal granularities. And as a result, they give you further out forecasts, they give you nearer forecasts, so on and so forth. Now, what does the emulator do? Well, these things can be slow to run. So what you do with the emulator is you train the emulator on the simulator. So the simulator has certain inputs and certain outputs. So I don't know, level of carbon you put into the atmosphere could be your input, number of degrees increase in temperature in 100 years' time could be your output. And what you can do is replace this complex simulator, which is including the physics, with like a machine learning or a statistical model that basically says, well, for this input, that's the output I expect. And you're just making now the sort of typical machine learning smoothness assumptions that you might make. So the nice thing, though, is if you've got an emulator, you can start calibrating your simulator to the real world, because a very common question in simulation is, how good is my simulation? How does it map back to the real world? So you can do things when you start emulating by not only modeling the simulator itself, you can also build more traditional machine learning models that model the real world, and you can try and capture how your simulation is departing from the real world because it's making approximations on spatial or temporal scales. And then you can include different levels of fidelity of simulator. Now, this is called multi-fidelity emulation. By the way, another word for this is surrogate models. So I was in Sheffield for a long time where they tend to use the term emulation, but surrogate modeling is another common name for this type of modeling. So multi-fidelity emulation, now your machine learning model is actually trying to learn from different levels of granularity. It's trying to learn the difference of these different how these different simulations behave in practice and trying to relate it to the real world. Now, the key point is you can choose to interrogate your emulator instead of interrogating your simulator. So if we take things like Bayesian optimization, which is very commonly used in machine learning now, you can view it as an example of this emulation process. In Bayesian optimization, you build an emulator that replicates the system you're trying to optimize, and you attempt to optimize the emulator directly, but you make a choice sometimes to revisit the simulator. Here, what I'm proposing is you do that sort of thing, but you revisit the simulator at different granularities, and you potentially revisit the real world. That's where it sort of starts to draw parallels between what's going on in probabilistic numerics, where the same type of decisions are made. Should I go to the real world, run one simulation at different granularity, run another simulation, or just rely on my emulation as it currently stands? Now, I view this emulation as a very sophisticated version of what's governor, of that centrifugal governor that we saw before. That's being tuned by hand by the engineer expert. I think we can do better than that by deploying these things virtually on demand in order to answer the questions we're interested in. And they give us the type of abstractions we need to give us that systems understanding. So to hopefully capture things like the hurricane in the weather. Okay, so I'm going to play a little example of this. We did, when I was at Amazon, we did this type of stuff a lot. And this is one of the most beautiful things we did. So this is Prime Air's drone, and it's doing vertical takeoff, and it's going to go into, in a moment, horizontal transition. So that transition there, which looks very elegant, is the hard thing to control. So underpinning that, and I should say that these are the real people that David Morrow, Paul Viola, and Gur Kimchian, who led the team. But Paul Viola's team, Paul Viola led the technical side, and David Morrow was leading the work in terms of the control side, where they integrated emulators in, and I can't go too much into the details because I'm not sure how much I'm allowed to say, but fundamentally what's going on there is we emulated this system using things like, we're using everything you imagine, computational fluid dynamics, wind tunnels, so on and so forth, and provided the sort of what's governor to enable the control of that transition. And it's about to go through the reverse control. So this is at its end here, that it's going through the reverse thing, it's going from horizontal to vertical, and that's the difficult bit to control. But it's being done by using machine learning techniques as surrogate models to operate the equivalent role to that the centrifugal balls were playing in the governor in the engine. So that kind of works in practice. And I think it's a really, really useful way of doing sort of engineering. If you want to see more about like the constraints, there are under a number of, the reason you go for that design is because you don't have enough energy to hit all your constraints to fly vertically everywhere. You need to fly horizontally to go the distances you need, given the battery requirements you have. And all those requirements are in this talk by Jeff Wilkie, who was the CEO of Worldwide Consumer, where he launches that drone, which is not flying commercially at the moment, but that's all down to regulatory issues. It's not down to the technical spec. That's also done. We hit those targets. It is a beautiful thing. It looks like a TIE fighter, doesn't it? I think, first time I saw it fly and knowing that our algorithms had contributed, and as I should say, it's Paul Viola and David Morrow, the ones really responsible, but our team had contributed, it made me quite emotional. Even if I'm not sure whether I really want drones delivering things to me or not. Still, I want to sort of map that onto another problem and show the diversity of which you can deploy these things. And this is another thing that we were looking at when we were at Amazon, and go to something completely different that seems initial perspective very, very different from that first objective. And that's a buying system, which is sort of the heart of, so the team, when we were at Amazon, we moved to supply chain, because basically supply chain is, to me, I find it fascinating. It's so funny how everyone wants to do like object detection and all these other things, when I don't think the complexity of those systems is very much. It's great that we can do it now, but the complexity of these systems, of these integrated decision-making systems is really, really interesting. I think a lot of the sort of issues that we face in building genuinely intelligent decision-making systems comes up in supply chain. But I'm going to give you a very simple perspective on Amazon supply chain. So what they're trying to do is they're trying to forecast the demand for different products, and I've put the little box up here. And they're trying to match that to the supply. So a colleague of mine had this wonderful way of describing supply chain. He said, the magic of supply chain. He said, well, he told this story. He was from Bombay, but he told the story of if you're in Kerala, on those rivers that they use to film Apocalypse Now. He said there's a guy down there who sells coconuts, and he sells coconuts by the river. And every time you ask him for a coconut, he climbs the tree, pulls down a coconut, sells you the coconut. And then when the tree he's selling under runs out of coconuts, he moves to the next tree down the bank. And then he would say, that's the shortest supply chain in the world. And he had this wonderful laugh. Narayan was his name, and he was a supply chain expert. And he said, now the magic of supply chain in the real world is making you think everything grows on trees like that. So the objective is to give that experience that you're getting from the coconut salesman with the very short supply chain by balancing the resources you have to distribute goods from as many suppliers as you can manage to as many customers as you can manage. And really that's what Amazon's supply chain is entirely trying to do. So it's trying to sort of minimize the resource needs to match what people want to what the supply is from manufacturers by storing them ready to go. But the cost of storage costs something. So you basically don't just have a demand forecast about what you're going to need to sell. You also have to have a supply forecast about what you expect, how long it will take to supply these given items. And then you also need to understand your cost basis, how much it costs to store these different items and how much value there's. Items even bring value to the supply chain by being there, because there's certain items that people will know that they can buy, like in supermarkets, they're called loss leaders, things like milk that just have value from being there, because you go down to the co-op, you buy your milk there, and when you're there, you buy something more expensive. So you get these loss leader things. So there's all these cost basis things going on, and you need to combine all those things, and basically the supply chain system makes purchase orders automatically based on its understanding of the demand, the supply, and the cost basis. So it targets a particular stock. And each of these things, this is the supply forecast is a machine learning system or a statistical model, whatever you want to see it as. The demand forecast is a statistical model. Your cost basis is bringing a number of different statistical models together very often. And the stock will be an operations research model, right? The optimal stock, given all these things, is often based on an operations research. A lot of the stuff in supply chain is operations research. You can tell that machine learning is nowhere near as active as it needs to be in decision making, because there's such a poor interface between OR and ML at the moment. It shows that we're not active as we should be in these type of decisions, because OR is what dominates on these type of economic decisions. And it's sort of funny how absent it is from our conversations in general. So this would be done by OR, the optimal stock level, something called the news vendor problem. And now that code base is typically written in a way like this. So actually, initially, a long time ago, people would write code which includes all these different components in order to deliver this solution, right? So you would have a bit of code that's doing a demand forecast, some cost predictions, supply forecast, purchase orders. And that would be a monolithic software base. But one of the things that's happening in software engineering at the moment is the move to what we would call a service-oriented architecture. And this is kind of very exciting for machine learning. So what you get in a service-oriented architecture, and this is how most machine learning models are now deployed, is that each of these components, and I've drawn them in this way that I would draw for a systems engineer, that if you ask for a particular, so within the ecosystem of Amazon, we could ask for a particular item like a coffee cup. We can say, what is the demand for that coffee cup? And there's a service that will give us a demand forecast. We can then ask, what is the supply forecast for that coffee shop? And there's a service that will give us supply forecast. We can merge those two together. And then we can say, what are the cost predictions for the coffee cup? We can merge those three together. And then that feeds a system that decides on what the right purchase order for the coffee cup is that week. Okay, so that's how the whole thing's working. Now, what that is a composition of decisions. Like, we could write this composition in some different ways, but what it ends up with is a sort of composition of all these sort of machine learning models that are going into what is the current stock level of your coffee cups. Now, the challenge with that is you're making multiple decisions in multiple places. And it turns out that while we can have teams that can build each of these individual models very accurately, as we start composing these decisions together, when something goes wrong, we very often don't understand what's gone wrong, where it went wrong. And you start needing to do causal analyses on these systems. But what's happening at the moment is we're not building them in such a way that it's easy to build those causal analyses on the fly. So this is a phenomena that I was trying to describe what this phenomena was, and I came across this term Jonathan Zittrain uses, that he says intellectual debt. So intellectual debt, I really like it. When we're building these complex AI systems, we basically end up with a set of composed decisions where we understand each individual decision, but we don't understand the composition and what results. So the technical debt, which is another thing known in machine learning, is this challenge that you build your system too quickly, and it's very difficult to maintain because you've not built it in a solid engineering way. So that also happens in ML systems. But intellectual debt, even if you've got rid of your technical debt, you're maintaining things as well. Intellectual debt is you've built a system you can't explain. So technical debt is the inability to maintain your ML system in practice. Intellectual debt is the inability to explain your ML system in practice. Okay, and that comes from this sort of whole process of separation of concerns, which is how we build large-scale complex software systems today. Nothing to do with machine learning, but it's also how we're able to ship machine learning systems very, very quickly. So I think I've covered all that. So one of the big agendas I'm interested in is how we deal with that in practice. And you won't be surprised that I'm going to come back to emulation here. So I think the problem with these code bases is not just how they operate individually, but they start to be viewed as simulations within the ecosystem. So once you've got all of this in code, people will do counterfactual simulations on this code, but it's very, very slow to run. And you get the same problem we had with the game of life. You get these emergent phenomena occurring that are very, very difficult to spot and occur at different times and cause you major problems. So one of the agendas I'm very interested in the group is what I would call deep emulation, where you start chaining these emulators together and you deploy them on demand to answer particular questions and to deal with the complexities of this vast system you're dealing with. Something that I think is very interesting in this case is when you combine that with, say, counterfactual analysis. So you end up with a sort of counterfactual emulation and you're moving between the simulation and the emulation. And I call this agenda auto AI because I think it's what we need to do in order to deploy, maintain, and explain the large-scale systems we're doing, but it's intimately connected with that ML for science ideas. So I'm going to sort of finish there, but Philip already kindly did this for me, so I want to make a plug for the Accelerate program, which we're definitely going to be partnering with Tübingen, which is the sort of Cambridge version of the ML for science that you're doing in Tübingen. And I think that there's a close connection. This is, for me, ML in the physical world, it appears in science as well as it appears in the supply chain, or it appears in when you're trying to design those sort of drones. The same questions keep coming up again and again, which is why my personal interest is steered towards emulation, although, of course, there's many other interesting things we can do, like feature representation when doing machine learning for science. And I'd also, if you are interested in what I just described, it's one of the great pleasures of starting at a new university is that if you get in quickly, you can propose your own courses. And so we did this course called Machine Learning in Physical World, myself and Carl Henrik, that's freely available online, where we basically go through the philosophy of how you do this, starting with the nuts and bolts, going through things like Bayesian optimization, which are examples of doing this in practice that are quite well known, and trying to extend it to ideas like multifidelity emulation. If you found what I was talking about interesting, but because I gave you no technical details, you're thinking, how on earth am I supposed to do that? And I'll end there a little bit over time for see if there's any questions.